Hey guys, myself Pattabhi Kumar Kone. I'm studying CSE Core in Vellore Institute of Technology, Chennai campus. Today I'm here to discuss about my topic, and the name of my topic is applications of context-free grammar in speech recognition. So first of all, what is context-free grammar? It is a notation used to specify the syntax of the language. Context-free grammar is used to design parsers. Has lexical analysis generates a string of tokens which are given to parser to construct parse tree. But before constructing the parse tree, these tokens will be grouped so that the results of grouping will be a valid construct of a language. So to specify constructs of language, a suitable notation is used which will be precise and easy to understand. This notation is called as context-free grammar. And now, let's have a look at the notations used in context-free grammar. Formally, context-free grammar can be defined as a four-tuple where V is finite set of non-terminals or variables, and sigma is a finite set of terminals, and P is a set of productions or set of rules, with each rule being a variable and a string of variable and terminals. S is a starting symbol, and G is context-free grammar production is a form of A stands to alpha, where A belongs to V and alpha belongs to V in direction sigma. And now let's have a look at the what CFG means context-free grammar consists of. So context-free grammar consists of a set of replacement rules, each having a left hand side and a right hand side, and two types of symbols, variables and terminals. LHS of each rule is a single variable, means which has no terminals, and RHS of each rule is a string of 0 or more variables and terminals. A string consists of only terminals. And now let's have a look at the capabilities of context-free grammar. There are the various capabilities of context-free grammar. Context-free grammar is useful to describe most of the programming languages. If the grammar is properly designed, then an efficient parser can be constructed automatically. Using the features of associatively and present tense information, suitable grammars for expressions can be constructed. Context-free grammar is capable of describing nested structures like balanced parentheses, matching begin end, corresponding if then else, and so on. And this is how the Chomsky hierarchy looks like. The containment hierarchy of classes of formal languages. So first it starts with the regular, which is small of size, and then the context-free grammar comes, and then the context sensitive, and the last one is recursively enumerable. And now let's have a look at parsing. Parsing is the process of taking a string and a grammar and returning a parse tree for that string. It is completely analogous to running a finite state transistor with a tape. It's just more powerful. There are languages we can capture with context-free grammar that we can't capture with finite state machines. And now let's have a look at the ambiguous grammar, and first discussing about the definition of it. Let G be a CFG, then G is said to be ambiguous if there exists an X in L of G with greater than 1, which means the leftmost derivations. Equivalently, G is said to be ambiguous if there exists an X in L of G with greater than 1 parse trees or greater than 1 rightmost derivations. And the point to be noted, given a CFL L, there may be more than one CFG G with L equal to L of G, some ambiguous and some not. And now the other definition is let L be a CFL if every CFG G with L equal to L of G is ambiguous, then L is inherently ambiguous. And now let's have a look at the example for ambiguous grammar. So here is one of the example of ambiguous grammar, like E equal to, they given some numbers like 0 to 9, and it also consists of plus, asterisk, commas and all that stuff. So we can do this in two different ways. Like if we can do it in two different ways, and if left hand side equal to right hand side, then it is a ambiguous grammar, as we can see in the picture. And now let's have a look at the patch tree. So there are two patch trees, like first one is 1 and 2, and here we taken the example of 3 star 2 plus 5. So two patch trees, which means star on top and plus on top, and two leftmost derivations. We have done two left derivations, therefore these two given grammar is ambiguous, so we can say in that way. So this is 1 and this is 2. And CFG parsing for high speed network applications. So this all comes under the applications of context-free grammars. So the first one is CFG parsing for high speed network applications and data processing, natural language processing, human activities recognition, and every context-free grammars can be converted to a parser, which is a component of a compiler and identifies the structure of a program and converts a program into a tree. And now let's discuss what is speech recognition. As you can see this from the picture, the task of speech recognition is to convert speech into a sequence of words by a computer program. As the most natural communication modality for humans, the ultimate dream of speech recognition is to enable people to communicate more naturally and effectively, as we can see in the picture. In speech recognition systems, a computer system attempts to identify a sequence of words from a speech signal. One way to improve the accuracy of the recognition is to limit the recognition to a set of selected phrases. This is typically done by limiting valid recognition hypothesis to phrases that are found in a context-free grammar, that is CFG. And now let's discuss about the method of managing grammars used in a speech recognition system, that is compressing. So loading a first grammar in a context-free grammar engine and then implementing an engine independent SR interface between the CFG engine and a speech recognition engine, which we call as SR, communicating words in the first grammar to the SR engine through the SR interface, notifying the SR engine through the SR interface of rules in the first grammar, representing the rules in the first grammar to the SR engine through the SR interface, and then receiving rule queries from the SR engine through the SR interface, and then representing the first and additional grammars to the SR engine through the SR interface as a single grammar. And 8th point is communicating words in the additional grammars to the SR engine through the SR interface, and then notifying the SR engine through the SR interface of rules in the additional grammar, and finally representing the rules in the additional grammars to the SR engine through the SR interface. And this is what the flowchart shows, as we can see in the figure 6. So what I have said, they are represented in flowchart manner in figure 6 and 7. So figure 6 describes a flow diagram illustrating how a speech recognition engine builds an internal representation of the loaded grammar. As we can see, 424, 426 and 428, so it's going in an order. And figure 7 is a flow diagram illustrating how grammar context is changed in accordance with an embodiment in the present invasion. So figure 7 shows us in detail all the steps, like starting from the 430 to till it goes to return. As we can see from here, so grammar GI will be loaded, and then addition calls, and then G1 is passed, and any change of context. So if there is a change, then we'll be going to yes part, like we'll be proceeding in this manner, and if no, we'll be going to CFG engine calls SR engine, and then finally we returns it. So this is what this figure 7 describes. And now the present invention includes a context-free grammar engine which communicates through an exposite interface with a speech recognition engine. The context-free grammar engine in one illustrative embodiment handles loading and unloading of grammars, as well as maintaining a desired invention state of the grammars which are loaded. Further, the context-free grammar engine represents all loaded grammars and their corresponding activation states as a single grammar to the speech recognition engine, as we can see in the figure. And now let's have a look at the background of the invention. So in speech recognition systems, a computer system attempts to identify a sequence of words from a speech signal. This is typically done by limiting recognition hypothesis to phrases that are found in the context-free grammar, which we call it as CFG. In the past, applications which involved speech recognition engines communicated directly with the engines. And now coming to the conclusion part. Thus, it can be seen that the present invention significantly reduces the burden on both SR engine and application. CFG engine handles loading, unloading, activation or deactivation and invalidation of grammars. CFG engine also handles adding and deleting words and rules from dynamic grammars and loading multiple grammars. CFG engine also parses results returned by SR engine and generates a rich result which is provided to application. The SR engine simply views the information provided by CFG engine. 212 has a single grammar which has rules and words that are independently added, deleted, activated, deactivated and invalidated. In this way, SR engine simply needs to recognize speech based on a speech signal input and need not concern itself with all the various tasks performed by the CFG engine. And so in this way we come to an end. I thank each and everyone for watching this video. Hope you have a nice day. Thank you.